very much for the introduction. Just we go. I do have a couple of disclaimers to make. I apologize if I do start yawning. It is very early here. I have had as much coffee as I can, but I'm sure we'll get through it. Also, I'm sorry about the lighting situation. If the sun does come up, I'll turn the light off and you should be able to see me better. Feel free to interrupt me with questions. I'm only working with one screen, so if there is a question, can somebody please just make some noise instead, because I won't see the little hand pop up. Today, I've thought I'd give just a bit of a big overview of methane genetics in Australia, starting with a little bit of background on AGBU and myself, putting methane into context in the Australian agricultural system, go over a brief history of all the methane research that has been done in Australia. I am going to keep that brief though. Then I really want to talk about sustainability indexes. We have a really cool example at the moment with the beef industry, which has just been publicly released. And then I'll go into some of the more experimental and trait development work that we're doing, especially revolved around the sheep industry. For both the sustainability indexes and the trait development, we have comparable examples with both sheep and beef, but I'm only going to present one species because they're similar stories. And then I'll go into a little bit more into the next steps in actual implementation for the Australian industry, and a little bit on the global perspective there as well. So starting with the background on a little bit about AGBU, if you don't know who we are and what we do, and how I fit into that as well. So AGBU, we're very close to our 50th birthday. We have 30 full-time staff and 10 PhD students, and we really have an aim of providing practical application of genetics for the Australian livestock industry. The majority of our work is focused on cattle and sheep, but we are the main facilitator for the pork industry in Australia as well. That's interesting because the Australian pork industry and our quarantine measures means that there is no importation of pork semen or other live genetics into the country. So it's all closed population. We've also done quite a lot of work with the goat industry. Bees have started to become a much larger topic, and elsewhere we see a little bit more interest in other insect industries, especially around feed for the poultry and pork industry. We also do quite a lot of work with aquaculture, and we do also work with crop and tree species as well, particularly canola, or I believe you call rapeseed. So one of the main functions that Australia has is the facilitation and development of our national genetic evaluations. So we do that for both the sheep industry. For the sheep industry, we actually run those evaluations ourselves, and we provide those breeding values for publication. We run that every fortnight, and that includes 700,000 genotype sheep, 500,000 of which is merino. So in Australia, 80 to 85% of the population has a merino background. And in that single step multi-trait evaluation, we have over 80 traits, including production traits, quality for both meat and wool. We also have health and welfare traits, and we are starting to add sustainability type traits such as methane, heat tolerance, and etc. For the beef industry, that's a little bit different. While we facilitate the development, the software development and the running, we don't actually run those evaluations ourselves. That's done through ABRI. But we provide those services for 40 beef breeds across 14 countries. And at the moment, the Australian Angus evaluation has close to 500,000 genotyped animals, and that's rapidly increasing as well. At the moment, for both the sheep and beef industry, we are working at turning those single-step evaluations into multi-breed evaluations to have a crossbreed evaluations. That's facilitated mostly through large reference population projects. I can talk a little bit about that if there is interest. And these evaluations are becoming quite large, so we also have a lot of focus on improving those through computational efficiencies. The other main thing that AgBoo works on is the development of selection indexes and software to facilitate those. So in the sheep and beef industries, that's through the programs Sheep Object and Breed Object. These basically simulate the entire flock or herd and the individual animal's growth and feed intake across a lifetime. And yeah, it's quite a very good system for developing indexes. And really importantly, we just started releasing publicly the first sustainability indexes. At the moment, those are within breed societies, so they're not technically available for breeders, for the public to see, but breeders can use those in sales. They will be released as a full public version, hopefully before Christmas, but definitely next year, with other breeds close to follow. Basically, this allows this software allows not only for individual breed associations or societies to develop indexes with us, but we can also do that for individual producers as well, especially if they have their own breeding objectives. And we see that this is an important step for those leading breeders who want to include methane in their breeding program. So I think that the bio did a good job of explaining where I come from and what I do, but I did spend a lot of my time during my PhD in Armidale at AgBoo and the University of New England. And while I was in the Netherlands for 6 years, working on similar methane projects in the dairy industry, I always had a pull back to Australia. And when I decided it was time to come home, I knew that Armidale was the place that I wanted to go to. So now I'm basically the research scientist that works on anything to do with sustainability across any species. And that's mostly through developing those sustainability indexes. And the other 50% of my time is developing those methane traits based on the large amount of data that we're building in our methane reference populations. I tried putting a prompt into Gemini AI to have a look at what it thinks methane production in Australia looks like. I don't think that AI will be taking our jobs anytime soon. But anyway, moving forward, I thought that I would just share how agriculture produces about 20% of the global methane inventory for Australia. I tried to compare this to Canada, but I couldn't find an estimate where it excludes fertilizer and fuel use in Australia, whereas in Canada, it looks like all I could find was where they've excluded the fuel use and fertilizer. So I think that your estimates are around 10%. So I think that from livestock, maybe we're getting close. That far on the right, the green one, that's the amount of greenhouse gas that's been reduced based on land use changes, and that's where the majority of Australia's reduction in contribution to global greenhouse gases is coming from. But from the beef and sheep industry, we see that the majority of methane in the agricultural industry is produced by beef cattle. We have a lot of them. But yeah, that's around 10% of Australia's 10% of Australia's greenhouse gas contributions in 2023. That number has actually been coming down as the herd size has been decreasing over the last 20 years. We also have about 3 times more sheep in Australia than we have beef, but luckily they produce about 10 times less methane per animal. But that's still a very large source of methane in Australia. So there is a large focus on reducing that for both species. Putting a little bit of context around where that methane is produced, we have the production system sort of divided in Australia, with the northern system, which is your more tropical, subtropical climates. Those top 2 photos are actually from the same area, different times a year. And then on the bottom, we also have sort of showing that the southern, more temperate climates are also very variable. They can go through droughts and can be very hard for animals to get through. Yeah, but we also see that the majority of the sheep production is in the southern hemisphere, and the majority of cattle production is in the north, but there is also a lot of beef produced in the south. Looking a little bit about the brief history of methane research in Armidale. So this is on the left-hand side is the respiration chamber facility that the University of New England operates. Currently, I believe they're running 10 respiration chambers. It is the largest respiration chamber facility in the world. A lot of the feed additive validation trials are done at that facility. So the sort of Bovaer type additives are tested there. It's also where Greenfeed validated their systems. If you're familiar with Greenfeed and the on-pasture measuring units or feedlot measuring units. At the moment, they also were used for the development and validation of the portable accumulation chambers, which I'll talk about in a moment. So in the middle photo, we have the respiration chambers for the sheep. I think that there's 12 of those. And again, they're mostly used for feed additive trials now, but they were originally used for the validation of the portable accumulation chambers. And I will talk a little bit more about those later on. So, as I mentioned, originally there was a lot of work on the feed intake trials, and that is what actually led into measuring methane. As hopefully we were aiming to use methane as a proxy for feed intake, as feed intake is very expensive, takes a long time to measure. That work flowed into the development of selection indexes, which I will talk about in a lot more detail in a moment. But basically that was for indirect selection of methane, but again, aiming to drive efficiency in feed intake. Then we saw around 2009, 2010, back when I was doing my undergraduate, the validation of packs and green feeds through those systems. Then there was, once the packs were shown to actually be a good proxy for methane, we started to see experimental projects that started collecting methane on individual animals, mostly from research and reference populations. Most of those experiments were limited to around 2,000 animals each or less, but that gave us our first estimates of repeatability and heritability, which gave us confidence to continue going forward and start getting preliminary estimates on the genetic correlations between other important production traits. And then we come to the current day where we're currently developing industry breeding values. And we have a large number of large-scale phenotyping projects to facilitate that. Yeah, so the portable accumulation chambers are a box, basically. The animals go in there, and if you know the volume of the box and the volume of the sheep, the duration that the sheep's in the chamber for, and the concentration, you can calculate methane production or rate of methane production. So it's a lot of work was done in Australia on those, and now we see that New Zealand have really taken that on board. They have their own breeding values based on the portable accumulation chamber, and we also see Uruguay has used these systems a lot as well. But before I go any further, I want to go back to those methane indexes that we produced for the industry. So this is mostly based on feed intake. From those feed trials that I talked about a moment ago, we found that there's a very high correlation between feed intake and methane production at about 80 to 85%. And a lot of the selection that comes out of these selection indexes is really driven by the fact that larger animals eat more, and animals that eat more, they produce more methane. So any way that we can reduce an animal's size will reduce methane. And that sounds counterintuitive for selection for production. But really, that's only if you're reducing the size of the animals that are sold. If we can reduce the production of animals from the female population, from those self-placing cows and ewes, we can have a large reduction in methane, since in Australia, 70 to 80% of methane is produced from that cow herd out on pasture. So that's really important in the fact that, you know, we can't easily provide feed additives to the majority of Australia's methane producing herd, because those extensive pasture systems that I showed in those photos earlier. So that's why we really think that genetics has a really large opportunity for methane mitigation in Australia. And I keep mentioning it, but, you know, we're quite proud of this, but we have started releasing those sustainability indexes through Breed Object. And we have a similar story developing with Sheep Object as well. Before I go any further, I want to make sure that there's no confusion around the two traits that I'm going to talk about. So we have methane production, that's like your grams per day trait. It's just net methane produced by the individual animal. And then we have methane intensity. So that puts the methane produced into context of the fact, hey, this is a byproduct of protein produced or fiber produced for consumption. So, you know, methane's not produced for no reason. And we find that farmers are much more likely, or breeders much more likely to listen if we put it into context of methane intensity. So at the moment, we're trying to provide information on both methane production and methane intensity. And that's something that we would also want to have more conversations with more international groups and our own producers around, you know, what is the actual breeding objective for methane in agriculture globally, and is it being fairly priced? So this is how the Breed Object sort of works at the moment for reducing methane. What I'm going to do is I'm just going to step through four or five important traits in the system and sort of what that's doing to the methane production intensity. So obviously, farmers want to be increasing their growth rates. So we're putting selection onto the weight of the calf, which is obviously causing an increase in growth. But animals that grow faster are larger, they eat more, so they produce more methane. So we see that methane production will increase with the current or selection indexes. But the methane intensity will decrease because the selection on those weight traits will have a larger impact on the denominator than the numerator. So we do have methane intensity improvements. And that's something that we've been trying to encourage farmers and the industry to really champion, is that, you know, the selection that's been done for the last 50 years has been improving methane intensity across that time. Unfortunately, that came with an increase in methane production, but again, putting it into context. At the moment in Australia, both for the cow and ewe sheep populations, is that we've found that there are a lot of complaints that cows and ewes have gotten too large. Sorry, I just need to. And that also comes with the benefit that if we select for smaller cows, will also reduce methane. So selecting for lower cow weight will reduce the overall methane production and will significantly reduce methane intensity. And remember that the majority of methane produced in Australia, 70 to 85% of methane is produced from that cow herd. So any reduction we have there will have significant reductions in methane overall. Unfortunately, there are some breeders who, well, I wouldn't say unfortunately, but there are breeders out there who are still going to continue to select for the larger cows. And that is something that we're trying to inform them more about, is that there are some people out there that don't think that a larger animal necessarily eats more, regardless of those, you know, sort of residual feed intake traits. The next one, reproduction. this is another important one because especially in the northern populations, so those tropical environments where we have a lot of Bos indicus, there are a lot of reproduction issues, fertility, conception, and well, we also have similar problems in the south, but it's much more noticeable in the north. But if we increase reproductive rate, it means that we'll increase the number of animals born, which will increase the overall methane production. However, it significantly decreases our methane intensity, because if we have a cow that fails to get into calf and rear that calf to weaning, that cow has produced methane for absolutely no reason, and it's it has a really big impact on that methane intensity side of things. So any small improvement in reproduction has a very large improvement in methane intensity. And anyway, it's still a really important trait for just a normal production system and breeding program. So we'll see a large emphasis on reproduction. Cow body condition score is a little bit more complicated to get around. So if we have say a herd that has a lower than average body condition score breeding value, we want to get that. We want to increase that. That means that the animal is probably going to be eating more, which means that it's probably going to be producing more methane. So that would make our methane intensity worse. However, if we improve the body condition score of our low cow body condition scores, it means that they're more likely to get pregnant. So it improves our reproduction. So if we, sorry, does that make sense? I'll just try and clarify that. I feel like I went a little bit in a circle. So cows that have a low body condition score need to eat more to get back into calf, into an appropriate body condition score to be mated and improve their chances of conceiving. So that will drive methane intensity because it's more likely to produce a calf for weaning. But that does come with the side effect that the animal eats more, so it produces more methane. I hope that clarifies it a little bit. I'm happy to go back over it again. But if we have animals that have, if we have a herd that has a higher than average body condition score breeding value, it means that they're likely eating too much than what they need to. So if we bring that down, what we do see is a reduction in methane production and methane intensity. But that doesn't come with the benefits of added fertility as much as it does for the low body condition score. So, as I mentioned, this is all facilitated through Breed Object version 6. The majority of it is focused on the feed intake, as that is currently our only real proxy for driving methane in the current indexes based on the traits currently recorded. So if we can reduce mature cow weight and reduce feed intake, then we're probably going to decrease methane production. And that's probably been happening with our current indexes as well, at least to some extent. If we select for increasing growth, increasing fertility, and increasing production traits, we'll see a reduction in methane intensity as well. So things that breeders should already be doing have already been reducing methane intensity too. So I've run some examples through Breed Object. So this is based on a grain finished production system, maintaining the current herd size, joining 200 cows a year, and I've got an average weight of 600 kilos per cow. I'm not going to show the results for the graphs, but it's pretty much an identical story. I'll go over this very briefly, but our main driver for reducing feed intake is basically increasing the cost of feed. We do that artificially. So you have your base price of feed, and that's what our current breeding objectives and selection indexes are based on, is the current cost of feed. But if we increase that cost of feed, it'll cause the system to go, hey, let's reduce feed intake to reduce our costs. And that's basically putting a pseudo price on methane or carbon. So what I have here is I've just pulled out three important traits to look at to start with. But we have the mature cow weight. I might just so this is mature cow weight. If we use our current indexes, so this is no increased cost on feed, we see that there is currently a small emphasis on reducing mature cow weight. We also see that we have a large selection pressure at the moment on calving ease. So that's our main trait for improving fertility. And what we see with that small reduction in mature cow weight, we're actually driving quite a significant decrease in the cow's methane produced, the methane produced by the cow. What I've done is I've added increasing costs to the feed, so sort of putting a price on carbon by driving, causing a reduction in feed intake. So higher prices at 10, 20, and 30%. And we see that, you know, as the cost of feed goes up, it causes more emphasis to be put on reducing mature cow weight. We also see that, hey, if we're feeding animals, we really want to get them pregnant. So we also see increasing emphasis on calving ease. And then the main driver, though, for this reducing cow methane is coming from that reduced cow weight. With the current system, if we use our current feed prices, a lot of emphasis is placed onto our production traits. So we've got yielding weight and finisher weight. And we see that, you know, in the current system, you should be selecting for higher growth rates. Higher and higher, but if we're selecting for larger animals, they are obviously eating more, which means that they're going to be producing more methane. If we do increase the cost of feed, so there'll be less emphasis, we are still going to improve our production traits. So yielding weight and finishing weight will continue to increase, at least up until we hit that 30%. Otherwise, that will maintain selection at the current level. But we see that it takes quite a lot to be able to bring the methane produced by those growing animals quite a lot. So it's not until you hit that high price of 30% that you're maintaining methane at the current level. I can also mention that 30% would be the equivalent of approximately $90 per tonne of carbon. And we've found that that's a little bit too much for producers and breeders to go for. So we see that there's more acceptance if we increase the price of feed by, say, between 10 and 20%. It's easy. The message to farmers is that, you know, you will still be improving your production traits. You'll be significantly reducing your cow weight, which will be driving lower methane produced by cows. And again, 75 to 85% of methane produced comes from the cow herd. I should also mention that 75 to 85% of methane produced by the cow herd, that does vary somewhat between the production systems and the breeds. So that's why that number changes sometimes. I'm going to talk a little bit more now about our current projects for the reference populations that we're building for both methane and feed intake. As I mentioned before, I'm going to focus on the sheep project, where we're trying to measure methane on approximately 10,000 animals across this project. In the beef, we have two projects, one based in the south, using a multi-breed project, the Southern Multi-Breed Project. They're recording approximately 8,000 animals. They're divided across pasture systems and feedlot trials. And we have a similar project in Northern Australia that's actually driven by the University of Queensland. And they're doing something similar, approximately 8,000 animals being measured for methane as well. So I really, really do want to thank our large team for the methane project, that this is truly one of those big collaborative projects. And a really big thank you to all of the breeders and technicians who have been collecting the methane data on sites. So the aim of this project really is to provide the Australian sheep industry with methane breeding values. And that'll be driven through the genomic reference population. So every animal that I talk about in this project has both a methane measurement and a genotype as well. So I sort of talked about the packs a little bit before. Basically, we have a box, and if you know the volume of that box minus the volume of the sheep, that volume of the sheep is basically based on a body weight that's taken within a week of being measured. And then if you have the duration of the recording and the concentration, you can calculate methane rate. Now, I talked a little bit about the history of methane in Armidale, and we saw that in the past, when those validation trials were being done, they were using this Vita-Foxbox combination. This is a highly accurate machine, but it is very expensive, and it requires a constantly burning flame. So we need technicians who really know what they're doing, and it causes quite an expense. In the last 5 to 10 years, we've seen researchers around the world and within Australia switching over to the Eagle device. We wanted to make sure that the data that we collected previously is usable with the Eagle as well. So we have been measuring with both devices, and I'll talk a little bit about that comparison later. But really, the bottleneck for us for providing breeding values has been having enough phenotypes, and it is a slow process of getting those measurements. So what happens is 24 hours, we go to a farm, and 24 hours before we start measuring methane, we take 72 animals from a flock and they're put into a holding yard. And in that yard, they have access to a high quality lucerne hay. Well, at least in practice, they do. Then we come back to the farm the next day, and 1 hour before we start measuring, 12 sheep are taken from those 72 and are kept off of feed. They still have access to water for an hour. So that's to make sure that the animal isn't on an upward methane producing trend. So basically, if an animal eats something, it's going to start ruminating and fermenting methane. But after an hour, you start coming down on the downward slope of that methane production. So we always want to make sure that we're on that downward slope or on the other side of that methane curve. I mentioned that we have 2 devices. So we also have 2 measuring points. So the animal goes in, 90 seconds later, the next animal goes in, 90 seconds later, the next animal goes in until we have all 12 sheep in there. Then we come back at 20 minutes and we measure methane on the first animal. 90 seconds later, measure methane on the second animal, so forth. And then we also have an endpoint measure where we measure at 40 minutes or 50 minutes. So we measure at 40 minutes for ewes. Because they're a larger animal, they're more likely to fill the box more quickly and deplete their oxygen and increase CO2. So that's also one of the reasons why we take a midpoint measure, is an animal welfare check to make sure that there is enough oxygen and not too much CO2 in the box. But it also gives us an idea of if the box has a crack or the devices aren't working. If we take that midpoint measure, our technicians know that, hey, this methane measurement is outside of the range that we would expect, and it gives us an opportunity to make sure that we get a second measurement at the 50 minutes. After each animal has been measured, at that 50 minutes, it's let out of the box. It immediately goes down into the yards and a rumen sample is taken. It's a very quick and easy process for sheep. So going forward, I will talk a little bit more about that correlation between the Eagle and the Foxbox later, but we're only going to be using the Eagle from now on. So a little bit of spoiler alert that obviously the Eagle is doing a good job and is comparable to the Vita-Foxbox. We've also stopped taking rumen samples now, just because we have 5,500 rumen samples in the freezer waiting to be sequenced. So we are sequencing as much as we can, but that is a very large cost that we can't cover at the moment. So at the moment, we do 6 runs per day. So once we finish those 12 sheep, the next 12 sheep come in. Because we're no longer doing the rumen sampling, we can bump that up to 7 runs a day. So that reduces our number of days per site, or increases the number of animals that we can measure per site. But we always aim to measure at least 500 animals per site. I talked a little bit about how we have historical projects. So there's, I think, 5 historical projects, and they were measured across 8 different research sites. Got over 5,500 animals from those historic records, from those historic projects. A lot of those projects did include repeated records. So they would either measure the animal and then 2 weeks later measure the animal again, or they would also have measurements across the lifetime of that animal. So at a growing phase, before pregnancy, during pregnancy, post-pregnancy, lactation, and pre-dweaning again. They also used to measure a lot on lambs, ewes, and rams. And as I mentioned, they used to measure with either the fighter fox box, or depending on the project, they may have switched over to the eagle. There used to be a lot more variation as well in the duration. So there is actually 10 and 20-minute measures, but they're not very useful, anywhere between 30 to 60 minutes. In this data, we've got 13 sites. That includes some of those research and reference sites that we used previously. But we've actually started adding commercial sites. So more than half the data in this project includes commercial producers. We've already hit 9,000 animals recorded, and we have plans of measuring another 2,500 animals over the next year. There was an overlapping project, so we do have some repeated records on those, and we've only measured on lambs and ewes. So in the analysis, I've used 17 sites, 14,500 animals. And because the recent data really doesn't include those repeated measures, and to avoid the complications of using a repeatability model, I've only used the first observation for any data set for an individual. So we do have some issues, especially around heterogeneous variance. So I want to point out this first site at the top here. It's got a very low mean and very little variation. This is a site where they were basically on a crop stubble. So they didn't have a lot of feed available. And when they went into the holding yard, when they were meant to have access to feed, they were also provided with bales of that stubble. And then we come over to the next 2 sites, and that's where we started providing high quality lucerne hay. So we see a large variation in the amount of methane produced. And so that's also driven around the behavior of the animal. So even if you put hay in front of the animal, it doesn't necessarily mean it's going to eat it. And some animals will eat a lot of it. The first step of dealing with this heterogeneous variance is I standardize the data based on the mean and the standard deviation per site. But we do have another method of using the CO2, the O2, and the methane and the body weight of the animal to predict the feeding behavior of that animal 24 hours before measure. And we include that in the analysis as well. I made some assumptions. So methane rate, we use the methane rate that's calculated from the boxes based on the concentration. So that's milliliters per minute. Some of the historic data was in other units that we converted back to. I've treated this as a trait of the sheep, but I have also treated it as a trait of lamb and ewe. But if I'm talking about all data, I've included both sheep, both lambs and ewes. I did not include any rams in the analysis. So we have that 25 and 50-minute measure for lambs, or 20-minute and 40-minute measure for ewes. And we see a very high correlation between those 2 different measuring points. So there is a possibility in the future that we'll only use the midpoint measure, and we'll be able to get through a lot more animals in a day. For the analysis, I've used the endpoint measure, whatever that may be, for that animal. And then for the Fighter-Fox box, we also see a very high correlation between those two devices. Where possible, I've used the Eagle measurement. But if they only had the Fighter-Fox box, I've also included that in the analysis. I mentioned that I only use the first observation for repeated records, and we are looking further at how to correct for date run location interactions. So the model I've used is a typical animal model, fits that date run location as a fixed effect, birth type, rear type, sex, age, and I realize that these are some old slides. I also fit the feeding level by site interaction. I sort of mentioned that a moment ago. So that corrects for the fact that some animals haven't eaten before they've been measured, and some animals may have eaten, 5 or 6 hours ago. We only know the minimum time off feed. We do fit the genetic groups because this does include crossbred animals and other breeds, but the majority of it is 80 to 85% merino across reference population and commercial producers. There is decent linkage between the commercial producers and the reference population. That's all based on the flock and breed. And the aim of this is to get the breeding values and project breeding values to start having discussions with farmers. I already mentioned that all the animals are genotyped, and we use a single step evaluation, and we use Wombat for that analysis. The reason we're going single step is that we want to make sure that this project flows through into our national genetic evaluations, which also uses a single step evaluation. I'm not going to spend long on this slide, but this site G, the heritability for that site, that corresponds to that top site that I presented on the previous slides with the low mean and little variation. So basically, if animals aren't eating enough, they're not going to be producing enough variation for us to capture the methane production for those animals, which means that we can't rank those animals. So I've actually excluded this site from some of the analyses. And we've changed the protocol for the future. So using all of the data, we end up with a heritability of 0.14. If I treat it as only a trait of the lamb or trait of the ewe, we increase that to 0.16 and 0.17 respectively. I've also done an analysis where I've removed all of the historic data, and I only record data that's included in this project or overlapping projects. And that has increased the heritability to 0.16 as well. So this is for both lambs and ewes, I should mention. It's coming from slightly reducing the residual. But we still think that there will be some benefit of using the historical data. We are working on the genomic validation of that at the moment. The recent data removed feed issues. That's the analysis I mentioned where I removed that one site that had no variation. And we do see that, again, the residuals reduced and the heritability has increased. So, yeah, we have changed our protocols based on those results as well. And then the final result here is from the fitting that feeding level interaction by site. So trying to correct the feeding behavior within the 24 hours leading up to the measurement. And that results in our highest heritability. This is the model that we're currently using and will likely be used for our discussing our project breeding values to partners. And we still need more discussion, though, whether that is correct for our final evaluations. So that roadmap of what we've come so far, we did the fundamental research, 15, 20 years ago. We have parameter estimates for methane traits, and we know the mitigation potential. That resulted in research indexes that, have been available for a long time, but have only started being released now through demand from industry. We have a lot of phenotypes now. Close to 10,000 animals have been measured. We have close to 15,000 animals in the analysis at the moment. But still more phenotyping for methane. It is a difficult trait to work with. Currently, we are publishing indexes with an indirect methane trait, but we really do want to get to that direct methane trait and have actual sustainability indexes that not only includes methane, but includes health, welfare, and other feed use traits and heat tolerance traits as well. So the next steps, we still have approximately 2,500 animals being measured. I didn't talk about the feed intake at all, but we currently have close to 2,000 animals on feed intake. These slides are a little outdated. We still expect another 2,500 animals to be phenotyped for feed intake as well. We do try and target animals that have methane measured and have those measured as close to possible as well. We collaborate a lot with New Zealand and Uruguay, and the Global Methane Hub is going to be helping us with collecting more data, and also the Australian Methane CRC will help drive that as well. So where we stand at the moment is that we are meeting those requirements for enough animals to be phenotyped. We currently have project breeding values. We haven't released those to the public yet. I'm working on the genomic prediction validation right now, but they will be available very soon. That'll lead us into research breeding values sometime next year. So project breeding values will only be released to people involved in the project. Research breeding values become publicly available. And we really want to be having as much producer engagement during this period as possible to have their input and say into what trait is used, and to help make sure that people are brought along for the story as well. We really want to avoid having bad faith actors, and climate and agriculture is a very sensitive topic. So we really want to make sure we do the right thing, and then that'll lead into Australian sheep breeding values, which is the gold standard for the Australian breeding industry. So we will be aiming to provide those breeding values to industry as soon as possible. Next steps, this project is the selecting for more methane efficient sheep. I'd mentioned that we have low methane beef, that's the project in the south, and reducing methane emissions and improving profitability in Northern Australian beef cattle. That's the Northern project, again, measuring a large number of animals. At the moment, we're really working on rapidly increasing our methane phenotyping, and we're trying to drive that through the Global Methane Hub and other large international collaborations. We expect that we'll have a direct methane trait in those sustainability indexes. Oh, sorry, that should be released in 2025. My apologies. If you do want to know more, feel free to email me or add me on social medias. Thank you very much. I'm probably going to exit the slides. Oh, sorry, one more slide. If you do want to come and visit us at AgBoo, you're more than welcome to stay or study with us. It is a fantastic part of the world. And yeah, you're very welcome to visit. Thank you very much.
I'll now open the floor for any questions from the audience here in person or online.
Yeah.
I'll have Bruno go first here in person, and then we'll move to Colin.
Okay, first of all, can you hear me, Dr. Michael?
I can. Yes, thanks, Bruno. Yes, I can.
Okay, so first of all, thank you for sharing all this expertise and this research done with us. My question is a kind of general question, I guess. I was wondering if we have two different situations. One breeding program breeding for methane production and the other breeding for methane intensity. How would be the output animal from these two different breeding programs? So which one would, which one would have the bigger animal, the more efficient animal?
Yeah.
Is it?
Yeah. Yeah, no, that's a good question, and it's actually something that we've been discussing quite debatedly. I spilled my coffee. Sorry. So that is a discussion that we've been having a lot, and at the moment, it's probably going to be the methane intensity trait, because for the methane production index to actually work and reduce methane production, you have to have a very, very high price on carbon. And, the breeders that are using it still need to be profitable. So unless there is actually a price on carbon or a premium for animals that produce less methane, those farmers that would be using a methane index based on production would become less and less profitable and eventually drive them out of business. So they would be more methane efficient and they would be more feed efficient, but they wouldn't be producing enough product to stay profitable. But having said that, if we really wanted to reduce our methane production and contribution to global warming, then the methane production index would actually be the one that we need to use. But I don't see that as realistic at the moment. Does that answer the question?
Yes. Thank you. Thank you very much, Doctor.
Okay, and we'll move on to Colin now. Colin?
To turn on?
Yeah.
Yes, sorry. Can you hear me now? Sorry, my mic didn't want to turn on.
Yeah.
Yeah, thank you, Michael, for the great talk and for getting up so early as well. I actually have two questions. The first one is kind of around the chambers that you have for the sheep, and I was wondering, just because I can see them being quite small and compressive, if there's any association, or if you've looked at it from, does the methane change at all over the period of time that you're actually recording it? Because I could just imagine the first time a sheep going in there, not being acclimatized and just being stressed, increasing metabolism, increasing methane that might be produced. So it's actually inflated. So if you have a more just easygoing sheep, for lack of a better word, their methane would actually be more representative than a very kind of stressed sheep.
Yep.
Or
thanks, Colin. Actually, you'd be surprised by how calm these animals are inside the box. That once you get the first animal in, it just stands there and is actually very calm. You know, there was a lot of work done on, heart rate, cortisol sort of stuff as well to make sure that these animals weren't being stressed during those validation periods. Talking about, does that change the methane production during the duration that the animal is inside the box? That's one of the reasons why we do go out to 40 or 50-minute measures, is that over that period of time, you remove a lot of that error around the animal behavior in those first few minutes. There is a constant release of methane by the animal as it's breathing. That's actually where the majority of methane comes from. And then it's the belches have peaks, but the majority comes from just the normal exhaling. Now, an animal that has stopped that process goes into a panting phase where it'll, and that increases the amount of carbon dioxide and reduces the oxygen at a much faster rate. That's why we take the 20 and 25-minute measure, is because if that has, if there is low oxygen or high CO2, or we observe the animal panting inside the box, then we know that we have caused stress to that animal and that the methane measure is likely to be invalid. Mm-hmm. That very rarely happens. Where during the time that I've been helping with the measuring, we released one animal from the box out of thousands.
Okay.
And yeah, it's a very rare instance that happens. And yeah.
Okay, perfect. Thank you. And the second one, if it's okay, Ella, really quick. And I apologize, maybe you touched on this, but I did get a call during when you were kind of talking about it. But with respect to the beef animals, were you saying that you guys are currently selecting to reduce mature cow weight while simultaneously selecting to increase calf weight? And I was just wondering, what does that relationship look like? Because it's kind of counterintuitive to me. And how much are you actually slowing down the genetic gain for calf weight, and then subsequently those calves have to remain in the herd longer and produce more methane? So I was just wondering what that trade-off kind of looks like.
Yep, no, you're 100% right. It is an unfavorable genetic correlation that mature cow weight and growth rate or growth traits of the calf are very highly correlated, but it doesn't mean that we can't make progress in both directions. At the moment, it's just that the animals are too large on the cow side. But it is, yes, it is unfavorable. We can drive both, but the reduction in the mature cow weight is still small enough that when still having significant increases in the production traits for the calf, we do provide multiple different selection indexes for the beef industry, and there are some producers who are not willing to make that compromise on the growth rate that they could have in their growing animals. So they refuse to select for the lower mature cow weight. That's a producer choice. how much you're willing to sacrifice for smaller cows. And we do find that, you know, the leading breeders are more likely to select the lower mature cow weight. And it's also become like an occupational health and safety issue as well, that, you know, farmers don't want to be dealing with large animals. And we also have a little bit of a different production system for the end weight of animals as well for the domestic market. You know, if we're exporting to the US, then, you know, they're more likely to be selecting for larger mature cow weight still to be driving their production for that market.
Okay, perfect. Thank you very much.
You're welcome.
I'll move to Flavio now. Do you have a question?
Yes, I have a question. Hi, Michael. Thank you so much for the nice presentation. Colin, I already asked the question that I was about to ask you, but I still have a question related with the chambers. So have you calculated the repeatability of measurements in the chamber? Like not within the 60 or 50 minutes, but in another test with the same animal?
Thanks, Flavio. Yes, that goes back to the historic projects where basically what would happen is they would get a respiration chamber measurement, and then they would immediately also get a portable accumulation chamber measurement, or vice versa. You know, they would do the inverse experiment where they would put them in a portable accumulation chamber and then a respiration chamber. They repeated those as well over multiple weeks and multiple stages of those animals' lifetime. It's a very high repeatability with the pack chambers. I think you're testing my memory, but I think the repeatability for a pack chamber is 0.85, and the correlation between a respiration chamber measurement and a portable accumulation chamber measurement is also around 0.85. You know, there is more error with the portable accumulation chambers. We know that, but it's better to have a measurement on an animal than no measurement. And unlike the respiration chambers, you know, the portable accumulation chamber really is a spot measure. So, you know, we could be anywhere on the methane production curve of that animal during the cycle of the day. But that is also why we use that 1 hour off feed in our protocol to make sure that we're on the downward slope of methane production. And that gives us a higher correlation with the respiration chamber validations and improves the repeatability of the measurements as well. I hope that answered your question, Flavio.
Yes, sure. Thank you. So another question that I have is about the model. Maybe I didn't quite got everything, but so you are including genetic groups, and probably the strategy is using the relationship matrix, right?
Sorry?
No, you are accounting for the genetic groups, and the genetic groups basically is to remove the difference between breeds, right?
Breeds and also the genetic groups are within between flocks as well.
Yeah, the missing parents, but the missing parents are linked to phantom breed groups. But my question is, I didn't see in your model anything to account for heterosis. Is that because there is no heterosis in methane production?
No, I am working on a breed adjusted G at the moment that I think will help account for that, but there are still some limitations with the data that I have, and the fact that a lot of this data is extracted from across different evaluations in our national evaluation. So I can't do everything in one go at the moment, but I am working on adjusting for that heterosis between breeds. So.
Are you expecting to see important heterosis?
I don't want to answer. I'm not sure. I don't think so. Sure. My gut tells me no. I think that the individual, like, I don't think that'll be a large enough impact for us to consider at the moment. I think that's the low priority at the moment. But don't quote me on that, please.
Yeah, no, I'm just curious about it because it's a novel trait to know. We like to.
Yeah, I should also mention as well. I don't think I mentioned it during the presentation, but in the genomic prediction side of things at the moment, we're probably going to just start with the Merino breed as well. For the genomic prediction validation work at the moment, I'm only working with the Merinos. They do represent over 90% of the data So
Yeah. Thanks, Michael. I will let other people ask questions. Thanks so much.
thanks, Flavio.
Thank you very much. And it's been a very interesting discussion, but I do think we have to close it for today. So I'm going to have everyone else just contact you via email if they have any follow-up questions. But thank you very much, Michael, for your time today. It was a wonderful presentation. And we will be posting this recording on YouTube, and we'll share that information with you as well. And we will see everyone back here next week for our last CGIL seminar of the semester. Thank you, everybody.
Thank you very much for inviting me.